Okay. So we are halfway through our course on antennas and radiating systems. So we'll finish backscatter cross section, effective area and backscatter cross section today. In the next class, we'll start with transmit receive systems. Uh, we're following DK Cheng and we'll be doing some exercises, uh, examples as well. I I had shared a couple of its assignments in the WhatsApp group. I'm yet to update all the course material on the website, but all the material has been shared in the WhatsApp group, and the recordings are available as a playlist on YouTube. So please let me know if you do not have the material. We'll sort it out. So in the previous class, we did internal impedance and directional pattern for receiving antennas, and we'll start with effective area and backscatter today. Okay, so I'll just skip all this. We did in the last class. So so we came up with this equivalent circuit for the transmit receive system, and then we separated the circuit into circuit at the transmitting end and the circuit at the receiving end, and then derived the expressions for Z11, ZG, ZL, the power um, ratio at different angles, which gave us the directional pattern. If there are any questions, you can on these you can ask them here or in the group. So we'll start from here. The effective area and backscatter cross section. Change this back to a pen or maybe a pointer. So in discussing the receiving antennas, it was convenient. Like let me change back to pen. So we have, for example, a transmitter antenna, and it radiates some waves. But when we receive it, for example, uh, this we have this antenna. This is the receiver. All the waves that were radiated from the transmitter will not reach this receiver, and then the waves which reach the receiver will all, not all of it, will be transferred to the load. So the portion of the waves, the fraction of the waves which are actually received by the antenna only reaches the your receiver load. So it implies that the the antenna will have, for example, this is the surface which is receiving the waves, but not all the waves which are incident on the surface were received. So therefore we can define a parameter which is an effective area, which receives the uh, which gives us the quantity, which gives us a quantified value of the antenna which is actually receiving. So that is the effective area. So not the entire area of the antenna will receive, uh, like not all the waves which are received on the antenna will actually be received. So some portion of it is received, and hence we define a term known as the effective area, which gives us the value which is the actual area of the antenna which is receiving. So let's continue our discussion. So the effective area, here's the definition. The effective area, AE, which we're denoting as AE throughout the discussion. So the effective area AE of a receiving antenna, it is the ratio of the average power delivered to the matched load. So the average power which is delivered to the matched load to the time average power density of the incident electromagnetic wave. So yeah, so a portion, so the time average power density of the incident electromagnetic wave. So some wave is traveling from the transmitted antenna or from somewhere from the space your antenna is receiving. So the time average power density, so the time average power density which is incident on this antenna, and the power which is actually delivered to the load, uh, power which so the average power which is incident on the antenna and the average power which is incident on the load, the ratio gives you the effective area. So we can write the power which is delivered at the load and the average power density which is incident on the area or incident on the antenna, and this is your effective area. So your effective area is equals to power which is delivered to the load by the power which is uh, this is the fancy P, average power which is incident on the uh, power density which is incident on the antenna. So this PL is the maximum average power transferred to the load under the matched conditions. So we're considering that all the power which was received by the antenna, not the incident, but the received power by the antenna is transferred to the matched load. Okay. So this load is matched. So if this load is not matched, then again there will be losses from the receive power from the antenna to the receive power at the load because of the load mismatch. So we're right now we're ignoring that. We're considering the antenna is matched to the load. Your antenna receiving antenna is matched to the load, and so there is some power, uh, average power which is delivered, average power which is incident on the antenna, and it is transferred to the load. So this what here is the receive power at the load. So maximum average power which is transferred to the load under matched conditions with the receiving antenna properly oriented with respect to the polarization of the incident wave. So and the other thing that we have to consider is, so the first thing was there is no mismatch between the antenna and the loads, because over here then you will lose some power. And the other thing is, for example, you have your transmitting antenna. So the orientation of the transmit receive system for, because should be such that we do not lose any power due to the polarization mismatch. So for example, if you have a dipole here and the other dipole is here, since if they are correctly oriented, they will come in, uh, they will be most of the this is the ideal condition for the receiving dipole. But if the orientation of the dipoles are not aligned, they most of the uh, signals which are sent through will not be received by the receiver. So there should not be any polarization loss or load mismatch. In that case, in the ideal case, we are defining the effective area. So we'll see that the effective area bears a definite relationship with the directive gain. So this is what we'll derive now. So I'll pause over here if there are any questions on the term or the definition of effective area. Okay. Okay. So if there are no questions, we'll continue. This is a little scribbled here. Let me just remove this maybe. Um, okay. So we'll derive a relationship between the effective area and the directive gain of the antenna. So in the last class, we came with this equivalent circuit, uh, where this was the open circuit voltage that is developed due to the incident waves. This is the generator impedance, uh, and this is the load of the receiver. So for the maximum power transfer, these impedances must be equal. The load impedance must be equal to the complex conjugate of the generator impedance, and let us say they are RB and JXB. So the maximum power delivered to the load from this particular equation that we derived in the last class. Uh, uh, so these are complex conjugate, right? So we lose the imaginary term over here, and again lose the imaginary term XP over here. So we get this. So this is the maximum power delivered to the load, and let us say RA is the input resistance of the transmitting antenna A. So let us say what we're trying to say is the transmit antenna is A and your receiving antenna is B, and this is RB minus JXB, and this is RA. So RA is the input resistance of the transmitting antenna. The transmitted power is then PT, which is equals to half I1 square RA. So this is the transmitted power. We have the delivered power at the load, and so and then combining the equations 109 and 110, taking the ratio, we get this expression, which is power delivered to the load was by the power which is transmitted from the transmitter. So here is this expression. So I'll pause over here, let you read the steps. If there is any confusion, we'll continue then. Okay, so we have taken the circuit. We have uh, we're trying to solve it for maximum power transfer over here. So Zg is equals to complex conjugate of ZL or vice versa. And we've calculated the maximum power at the load, the transmitted power from the transmitter. We've taken their ratio. From these two expressions, we got this. Combining these two, we got this. Okay, so when antenna B, so keep remembering this, the transmitter is A and receiver is B. So when antenna B is receiving, the time average power density of at B depends on the directive gain of the transmitting antenna in that direction. So the previous class, we saw that for any antenna, the the power which is radiated in each direction could be different, and so there will be some directional pattern around the antenna which gives us uh, power, the power density with in each direction. So so from that information we know that uh, and this is basically due to the directive gain in that direction. So if the antenna A is transmitting to or radiating, and there is we have the antenna B over here. So based on its directional pattern, we will choose. We have the directive gain in that direction. So we will use that in the expression. So the receive power, which is the power. So we had the power. We had the trans incident power, right? Power transmitted from the transmitter, which was incident. So we had the incident power, and we have the power at the load, but we actually need the power which the average power which is incident on the antenna B. So we have that, so the time average power density at B is equals to the power which was transmitted by the transmitter uh, uh, by the surface area and the directive gain. So this is the expression for PAV. And now using 12 and 7. So we have PL over here and we have PAV over here. So we gonna substitute this PAV into PL. So yeah, so PL is equals to AE into PAV. And now substituting this over here, we have AE into PTG dA upon 4 pi r square. Now taking this pi, uh, removing this pt from here to here, we have PL over PT is equals to AE GDA. And notice the subscript which is added B over here. So we are right now we're calculating the effective area of antenna B. So when we calculate the effective area for A, it will be AEA, and when we are doing over here, so we are using notation effective area for B. Effective area for B, GDA upon 4 pi r square. Now comparing 11 and 13, so 11 is over here, is 11 and 13. Comparing 11 and 13, we can um, we have this unknown, right? Z21. Z21 is uh, found out to be the radiation resistance of A, radiation resistance of B, effective antenna A, effective area for antenna B, uh, gain of the antenna A, the directive gain of antenna A, and pi r square. Similarly, if we were to if the transmit and receive were interchanged, so if B starts radiating and A starts receiving, in that case, we will have radiation resistance of B, radiation resistance of A, effective antenna area of A, uh, gain of the transmitter, which is now B, and pi r square. And since we know the media is reciprocal, so Z12 is equals to Z21 from reciprocity. So using 14 and 15 over here, we can give this relationship. So gain upon uh, gain of the antenna, uh, directive gain of the antenna divided by the effective area of the antenna is equals to constant. Okay, so this is what we get. Um, And since you have noticed, we have not specified any type of transmitting or receiving antenna. All this was just considering if this could be any antenna. Uh, the ratio of the directive gain and the effective area of the antenna is a universal constant. So that's what this case stands for. This is constant. Basically, it could be any antenna. It will the gain, the directive gain, and the divided by the effective area. It will be constant, and this constant can be found by determining the directive gain and the effective area of any antenna. So if we solve, so we'll do that in an example next. We'll try to solve it for one antenna, and then we'll get this constant. And once we have this constant, we can use it to calculate the directive gain from the effective aperture or effective area, or vice versa. So I'll pause over here, let you go through the steps that we went through. We calculated the power at the load. We calculated the power transmitted. We took its ratio, and again we calculated the average power which is incident on the receiver, and which is dependent upon the directive gain of the transmitter. We took the ratio. We took again calculated this ratio again and compared the PL by PT is two expressions, and got the expression for Z21. Can calculate again, we got calculated it for Z12, compared it to get this particular expression. So pause here. Let me know if you have any queries on this, else we'll proceed. Okay, so we'll proceed then. There are no queries in this. So we'll do an example now to find out the constant. So the question says determine the effective area AE theta of an elemental electric dipole of length dl. So we've already seen this figure before. Uh, dl, which is much smaller than lambda, used to receive an incident plane electromagnetic wave of wavelength lambda that is polarized in the direction as shown in figure 11.8. So this is the polarization. So we have already used this figure and like calculated a lot of expressions, including this radiation resistance, which will be used in this example. So if you can refer to the previous class text or the book to if you have any if you forgot the discussion or if there are any queries. So we'll use the previous knowledge to solve for the effective area. So let ET be the amplitude of the electric field intensity at the elemental dipole of length dl. So this length is dl, uh, and then the time average power density is PAV is equals to uh, square of the incident electric field upon 2 eta naught, the average power delivered to the mismatched load. Sorry, to the matched load. So they're the complex conjugate of each other. So PL is equals to half EDL sine theta square. So this is from the previous expression that we had, and now we're substituting that. So radiation resistance of the dipole is known. We will substitute this over here. This is known. Oh, sorry, ZL is yeah. So this was ZL over here. Now we're adding ZG conjugate to it, and yeah. So once this is solved, we get this expression EDL square sine theta square 8R 8RR. So the ratio of this PL upon PAV gives the effective area. So we have PL, we have PAV. We'll take the ratio, and this gives us eta naught upon 4 RR radiation resistance into DL square sine theta square. Um, Eta naught can be written as 120 pi. We have the value, the expression for RR over here, and then everything can be cancelled and out. So after simplification, this is what we get: a 3 upon 8 pi lambda sine theta whole square. So this is the effective area of this dipole antenna. So it is interesting to note that the effective area of the elemental dipole is independent of its length. So this is yeah. So if you notice, we do not have the dl term. We only have the lambda term. So the effective area depends upon the frequency or the wavelength that we are trying to receive, and it's independent of its length. Okay. So before we proceed, I'll just pause here if you want to go through the math. Okay. So we calculated the average power time average power density, the power delivered to the load, took its ratio to calculate the effective area. These two terms give us this term. So from this, one of the previous examples that we did in the initial classes uh, for the same figure that we saw before, we had got the expression for the directive gain of elemental electric dipole to be 3 by 2 sine square theta. So this we already this we know from the previous derivations, and now this directive gain can be written as 3 by 2 sine square theta. Now multiplying, dividing, so we can, like this, we have multiplied with this term over here, and then divided with this 4 pi and lambda square here. We just modified this term to look like this, and from this term, this resembles the effective area. So we can write this directive gain is equals to 4 pi upon lambda square times effective area. So from here we get the constant that we declared to be equal to this. So this indicates that the universal constant for this expression, right? If you remember from the derivation, the gain upon effect. effective area, the relative gain upon the effective area is equals to, we had said this is equal to some k. Now this is equal to 4 pi by lambda square. This is the constant. So now once we have the constant, we can, if we have the directive gain, we can calculate the effective area, or if we have the effective area, we can calculate the directive gain at that particular wavelength or for that particular frequency. So I'll pause here, let you read these two steps, very crucial, and if there are any questions. Okay, so now we have calculated the constant. So in case of thin linear antennas, the concept of effective area may seem arbitrary, because yeah, because most of the, like, the antenna area is actually equal to the, so this antenna length is actually, so this antenna length is actually the effective area. So yeah, so in case of linear antennas, they do not make a lot of sense. But if, for example, if you have a horn, so they will have this aperture which is radiating, or you have a patch. So this patch is that, in these cases you can actually get a very good insight of how much of the area that your antenna is using is actually radiating. Yeah, and we expect the effective area to be related to the effective length. So um, that is as well. Um, so the available power to the antenna load under matched condition is this. So this particular expression is from the circuit that we had. If you remember, open circuit voltage, we had ZG, and then we had ZL, for the receiving circuit, for the the circuit for the receiving antenna, and that so the power which is delivered to the load under matched conditions is V square VOC square upon 8R, and we have the power which is delivered to the open circuit, the voltage which is generated is equals to uh, the effective length into the incident electric field, which we saw in the initial classes. We can substitute that, and this gives us a relationship between the effective area and the effective length. So, so this is also a very useful expression. So the effective area is actually the 30 pi upon radiation resistance times the effective length. So if so this is a good parameter if you want to compare um, the for example, if you have a dipole and a horn antenna, and if you want to compare them in terms of the effective area or effective length, so you can calculate the effective area for the horn, effective length for your dipole, and then convert one of these terms and then see uh, which one of them is more suitable for your application. So that's about it for the effective area. So I'll again pause over here and let you go through these two expressions if there are any steps that you uh, want me to repeat. You know. Okay, so we'll proceed then. We'll now start with backscatter cross section, or also known as radar cross section. So the effective area, which we saw in the previous slides, relates the power received by the match load for a given incident power density. So, so if you intend to receive power in some load, and so what you'll do, you'll match the load, you'll make sure uh, you make sure that there is no polarization mismatch. So, and you have an antenna. So, this is the case when we intend to receive the power. But what do we do if we do not we do not intend to receive the power, or there is no load? Uh, so, for example, if there is some object, let's say a car. So this is just a car, and then let's say you have some uh, transmitter. So the waves will travel, it will hit the car. Some of it will be, or most of it will be uh, scattered. So for if it was an antenna, we have, and then we had some waves, and if the antenna received some waves, so we called it effective area, which is actually receiving. But for a car, we cannot use the term effective area because we are not receiving the waves which are incident on the car. Or what it is doing is it is scattering the incident waves. So for this we have the term we have this parameter called as backscatter cross section, or the radar cross section. Okay, so we call it radar cross section because we usually use radars for radio detection and ranging. That is where we send some EM waves. It strikes the object, it reflects back, and then we uh, do some maths and solve some equations and get the idea how far the object is, uh, and how fast is it moving and stuff. So, but we have to note that not all objects will reflect or scatter the wave in the same fashion. So, let's say if this is me, and then there is uh, a statue of me. Let's say I did some great teaching, and then they made a statue of me, which is, let's say, made of bronze or copper. So this is completely metal. So, and then there is some radar over here which is sending some signals. So the wave which is incident on me and reflected back to the radar. So the strength of the signal from which is reflected from me will be much, which will be not much less, but will be definitely lesser than the reflected or the scattered wave from my statue, which is completely metal. So there are different objects based on their orientation, based on their material. Uh, it will the reflected or the scattered wave. It will depend upon these properties. So in this case, what we can say is my radar cross section is lesser than the radar cross section of the statue. So let's just go through some the text and then we'll pause for questions. So when an incident wave hits a passive object that scatters the wave without absorbing energy, we define the backscatter cross section or the radar cross section. So this particular object is passive. That is, it is not a communication system or where there is an antenna or some receiving device. So this is some object which is not intended to receive. So this passive object, this scatters the wave without absorbing energy. So this implies that there are objects which can absorb the energy, and then so this is another research area which is absorbers. So if you have been to an anechoic chamber, you must have seen some cone-like structures which have some black thing painted on the corners. So these are known as radar absorbent material. So there is another whole research area on absorbers. So a passive object which scatters the wave without absorbing energy. For that we have this term called radar cross section. So the backscatter cross section of an object is the equivalent area that would intercept the amount of the incident power to produce the same scattered power density at the receiver side if the object scattered in. So okay, so a very long statement. This is trying to say that this radar cross section is a value which uh, which defines the so let's go through it slowly. So of an object is the equivalent area. So this is some equivalent area. It will be like unit will be minus meter square. Um, so this is an area. So let's say if this is me, and then this is this blackboard. Both of us will have some radar cross section, and this will be given in meter square. It will be some area that 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 would intercept the amount of incident power. So some if some electromagnetic wave, EM wave is incident on us, we would intercept some of it power and produce we will scatter it. And this scattering uh, produces same scattered power density at the receiver side. So let's say we have a receiver over here at the receiver side. If the object scattered uniformly in all directions. Uh, okay, so this is yeah. So the amount of power which was incident on me, and similarly this blackboard or some other my statue, all of us will scatter the incident wave. So and to quantify this, let's say there is a receiver. So the this ca what will be a good analogy? So there is some uniform object which could scatter the incident wave isotropically in all directions. So comparing it to that. Uh, yeah. So let's go through this statement again. So this is an equivalent area. So let's define an equivalent area, and this particular area can scatter uniformly in all directions. So we need to calculate this equivalent area relative to me or the other objects, which would so I also scatter the electromagnetic waves differently in different directions, so which is not isotropic. So there is other object which also radiates in or sorry, not radiates, scatters in different directions. So we need to calculate the effective area of an isotropic for an object which will scatter the waves isotropically in all directions. So the uh, so this effective area which would scatter isotropically in all directions, uh, the same is in a similar fashion as me is my radar cross section. So let's define the terms. The time average incident power density as pi, the time average scattered power density as ps, the backscatter or radar cross section as sigma bs, uh, and the distance between scatterer and the receiver r. So this means that the radar cross section into the incident power divided by the surface area around to towards the receiver. So this there is this scattering object, and then we have the receiver over here. So we had some incident power. This scatterer has a radar cross section of bs, and then we have this distance r between the receiver and the scatterer. So if we take a surface area through all around the scatterer, so its area would be 4 pi r square. So the power received at the receiver is ps. So the power received at the receiver ps is equals to the incident power into the radar cross section divided by the surface area we have taken per unit area. So this is the relationship, or rearranging this will give us the radar cross section is equals to 4 pi r square into the scattered power by the incident power. So we have to note that the scattered power is inversely proportional to the distance, and for large distance, the inversely proportional to the so this scattered power is inversely proportional to the distance between the scatterer and the receiver, and the sigma v does not change with r. Yeah. So this okay, not sorry. So this sigma bs into this p incident power by this is 4 pi r square, right? And this is equals to the scattered power, and the scattered power in itself, uh, the for EM wave, if you remember, when EM waves in their far field, it becomes proportional to 1 by r square. So this ps is actually some terms time r square. So these can get cancelled, and this implies that the sigma bs, or the radar cross section, does not change with uh, r. So I'll pause over here. If there are questions on radar cross section of an object. Okay, so we'll proceed then. We have defined the radar cross section. We will do one example as well, in which we calculate the radar cross section for rain. Um, droplets of water. That's what we'll do. So there is this definition of backscatter. Okay, this is very scribbled. Let me just clear this from the screen. Discard, present again. So there is this definition in the textbook. The backscatter cross section is the measure of detectability of the object target by radar, radio detection, and ranging, hence the term radar cross section. It is a composite measure depending on the geometry, orientation, and constitutive parameter of the object, and on the frequency and the polarization of the incident wave in a complicated way. Yeah. So there was this statement in the textbook. So this basically says that if there is an object, it will have its radar cross section, and this radar cross section uh, uh, is actually dependent upon the geometry of the object. For example, if the object is arranged in it is some sheet-like thing. Uh, um, yeah, if it is spread across so if it has a larger area, it could mean it has a higher RCS. But for example, if you change its orientation such that the incident wave does not like is not incident on the greater area, then its RCS would be reduced. Or if its material is changed from uh, metal to plastic, uh, its RCS will again reduce. Again, at certain frequencies, some materials will have a higher RCS than the others, and also depending upon the polarization of the wave, if it is reflected back. So the RCS is more complicated than this simple definition. It definitely depends upon the material and it's the orientation. But yeah, so this is so basically RCS, or the backscatter cross section. It's the detectability of the object. That's what we are trying to emphasize. So we'll do this example now. So this question says a uniform plane wave with electric field intensity EI, which is oriented in the Z direction, impinges on a small dielectric sphere, notice dielectric sphere of radius B, which is much smaller than the wavelength of the incident wave, and the electric constant epsilon r, as shown in this figure. So we have this sphere over here, its radius is B, and we have an electric field incident the incident wave is oriented like this. Its its electric field, the permittivity is epsilon r, and the incident wave has the wavelength lambda, and this lambda is much greater than say this radius. So assume the polarization produced in this sphere to be same as that produced in uniform static electric field, and to be given by so this polarization density is the polarization density is given as epsilon naught epsilon r minus 1 times E, and then this is again given by this expression 3 epsilon naught epsilon r minus 1 by epsilon r plus 2 EI. So this is the expression for polarization density, and we need to find the backscatter cross section. And then once we have this, we can use this to determine the backscatter cross section or the radar cross section of a spherical raindrop of its this diameter at this frequency and this is the dielectric constant of the water, mm, at 15 gigahertz. So let's do this. Since the induced polarization vector, the volume density of the electric dipole moment P is constant, it is said over here that assume the polarization produced to be same as that produced by uniform static electric field. So this is by the static electric field. So and this expression is over here. This epsilon is again known. So this turns out to be constant within the electric sphere. The total electric moment, the total electric dipole moment induced in sphere is of this radius is this expression. So the dielectric moment is volume times the uh, polarization density. Uh, so this is the volume multiplied by P. Now we were given the expression for P over here. We, we substitute this, and this is the electric dipole moment. Now the electric sphere acts as an acts electromagnetically like an electric dipole of moment P, as given in 1126. Um, yeah, so we have the dipole moment over here, and now we have this expression for small electric dipoles that uh, Q is equals to I upon G omega. Again, we know that dipole moment is can also be written as Q into dl, and the electric field is for small electric dipoles is given by this expression. So substituting the expression for I over here, um, we get Q into J omega, and then substituting Q uh, from this, we have the expression for electric field as A omega uh, P, which is the dielectric moment, dipole moment, by 4 pi E J B R. Beta is basically 2 pi by lambda, the impedance of the space, distance between this is the distance of the receiver, sine theta. So substitute so and once we have this P over here in this expression, we can substitute this P with this expression that we got in 11126. So if this gives us the expression for the electric field. So what we did was we have the expression for polarization vector. From that, we calculated the dielectric moment. Uh, dipole moment. And from dipole moment, we uh, we calculated the electric field. So we have the electric field now. Now using this, we from the dipole moment, we got the electric field. Now once we have the electric field, we can calculate the time average backscattered power density to be 1 upon 2 eta naught. Uh, this electric field expression. Now we substitute this electric field over here, and at theta is equals to pi by 2. So we are choosing one of the direct. So this is the average, right? So we get this. Now we have the power density, uh, and now the time average incident power density is 1 by half eta naught ei square. The incident field, and the scattered is also in terms of the incident field. So we just take the the ratio of the scattered power by the incident power, uh, and we get this expression. So this is the expression for the backscattered radar cross section for this spherical dielectric. I'll pause over here if there are any questions on this. So what we did was we had the polarization vector given to us. We use that to calculate um, um, the dipole moment. Um, Substituted the value of P over here, and from that, from this dipole moment, we calculated the electric field value. Um, Once we had the electric field value, we calculated the scattered power and then the incident power, and then using this expression, we substituted the value for the scattered power and the incident power, and we got this 11,130, which is the backscatter cross section. So we'll just quickly finish for the raindrops and then take any questions if you have, or close the class. So the second part of the question asks us, the B part asks us to determine the backscatter cross section for a spherical raindrop, and we have given the diameter, the frequency, and the dielectric constant. That's all we need to know. So this from A we have the expression for the backscatter cross section for dielectric sphere. So 4 is known, it is a number. Pi is known, it is again a rational number. B is the radius. So we have the diameter. Uh, Beta is 2 pi by lambda. So pi is known, lambda is known. Yes, we know this frequency. Again, B is the radius, and we know the diameter, and the epsilon is known. So everything is known. So for f is equals to 15 gigahertz, turns out lambda is 20 mm, B is 1.5 mm, which is much smaller than lambda. So we can use this expression. Uh, so once we substitute everything, we get sigma bs as 1.1.25 millimeter square. And if you take the ratio with respect to the space actual surface area, which is pi b square, so 1.25 by 1.5 square upon pi, it turns out to be 0.177. So this radar cross section, which is also an area, is much smaller than the sphere's actual surface area. So uh, this is uh, this implies that radars are actually very good even bad weather. So hence we use radar to detect aircrafts and for other applications. So radars are actually very good even under bad weather conditions. For example, if it's raining, it is cloudy, we can still detect the aircrafts um, uh, uh, at the airports you must have seen. So this is actually very so this calculation uh, gives us very good insight into the working of radars. Now, of course, we uh, had a lot of assumptions. The first one being that the raindrops are spherical, so they need not be spherical. Now, also, um, yeah, no, and this is not they're not spherical, and again, the the permittivity is taken to be 55, but this is almost constant throughout the frequency range. So all these approximations are kind of okay, and meaningful calculations of the backscatter from the rain require the knowledge of the rainfall rate and the distribution of the drop size. So again, drop size is also something we took this we took a 3 mm that could be within some range, but for, and again the rainfall rate does not mean that there is just one drop or two, three drops. It will be raining, so that will so this will all affect the calculations. But again, the assumption of this spherical shape and all this is fine. So this, if you do it more properly, it will still show that the radar cross section is actually for rain is much like very small as compared to their actual area. So this is fine. So we can use radars under bad weather as well. And all this is fine, okay, as long as when we make sure that the raindrop size is much smaller than the wavelength. So we have to make sure that we do not use a frequency range in which the wavelength is comparable to the size of the droplets. In that case, these approximations would fail. Yeah, so that's all we plan to cover today. The next class will start with transmit receive systems. So we'll look at the Frisk transmission formula. So I'll pause over here, and if there are let me know if there are any questions. Um, else we'll end for today. Okay, so if there are no questions, we'll stop here today, and I'll try making I'll try doing a class tomorrow or next weekend.